Okay, this is the 8th revision video for C1, and we're going to look at plant oils and their uses. Okay, so you need to be aware that some fruits, seeds, nuts, and are rich in oil. So you'll be familiar with olive oil, for example, and we can extract that oil and use it particularly for cooking. Okay, plant material is crushed, so anything we get like the olive, for example, will be crushed. The oil might be removed by pressing or in some cases distillation. You do not need to know any more than that in terms of the process to get oil from that fruit, seed or nut, but be aware that we can get it through some of those methods. Okay, so the vegetable oil we get out are really important foods and fuels because they contain so much energy. Okay, they also provide us with a great deal of nutrients, so that also makes them useful, but because they contain energy, it makes them really good fuels. Okay, and we often use these for cooking because they have a higher boiling point than water, which means you can get to much greater temperatures and you can cook that food much faster, because the oil, you can get it warm before it all starts evaporating out of your pan than you can with water. It also gives your food a completely different flavour, which is often preferred. The big negative though is it will increase the energy content of your food because you're cooking it in oil and not water, and oil contains a large amount of energy. So that's a negative. If you were to cook all your food and also fry everything, it would have a huge amount of energy, which would have negative impacts on our health. Okay, so that's what you need to know about oils, where they come from, how we can get them out, and the properties, if you like, of those, and how we use them in cooking. Okay, it then goes on to talk about emulsions and emulsifiers in this topic, which is an area where people tend to get a little bit confused. Okay, so if we look at oil and water, they don't mix. If you pour oil on top of water, it will sit there in a layer, okay, which you might see in your salad dressing, sort of separating it out. To prevent it from separating out, we can make an emulsion, okay, and emulsions are much thicker than oil or water, so it'd be an obviously much thicker solution, and you'll be familiar with them as an ice cream, paints, or salad dressings are all emulsions. Okay, they have better texture, coating ability and appearance to just an oil and water mix. And the reason they are thicker and they don't separate out is because they contain an emulsifier. This bit here is higher level, as shown by the H. So if you're doing foundation, don't worry about this bit down here. Emulsifiers bind together, if you like, that oil and water, so they mix together, and they're made up of a hydrophobic tail and a hydrophilic head. So a head that loves water and a tail that hates water. So if we look at a diagram here, the yellow is the oil, the blue is the water. So here we can see that water-loving head inside the water droplet in each case, and the water-hating tails going out into the oil. So by doing that, it binds the two things together and holds it as an emulsion and doesn't let it separate out like we've said there. So that's how emulsifiers work, okay, which isn't too hard to understand, I think, if you can visualise what's actually going on inside that emulsion. Okay. The other little bit you need to be aware, and this links into the topic we've just looked at with alkanes and alkenes in particular, is that vegetable oils tend to be unsaturated, which means they are not full of hydrogen because they contain double bonds, which remember we can detect with bromine water. So bromine will react with that double bond, bromine will lose its orange colour and become colourless. And what we can do, and again this is higher tier now, those unsaturated oils can be hardened by reacting with hydrogen. So what we're saying is we can react with hydrogen, remove the double bond, make that a single bond, and add in extra hydrogens around it. Okay, we need high temperatures, so 60 degrees C, and a nickel catalyst to do that. And the reason why is because if we look at a very simplified diagram, you can see that these chains here are lying much closer together because there's no double bonds. They're really neat. So all those single bonds surrounded by all the hydrogen. It's a very neat chain, which means the chains lie close together. So force of attraction is much greater. So to overcome it, you'd have to heat it a lot hotter. So hydrogenated oils or fats have a higher melting point. They tend to be solid at room temperature. So that would be things like your butters, your margarines. Your oils, like your olive oil, will be an unsaturated oil. They'll contain double bonds. They tend to be more kinked or bent in nature. The chains lay further apart. Force of attraction is weaker. So the room temperature tends to be enough energy to overcome that and turn it into a liquid. Okay, so we've melted it already. But if I want to take my olive oil, which is better for me, okay, than maybe butters, and I can turn it into something firmer and harder by adding more hydrogen to it, getting slightly straighter chains, so losing those double bonds, getting those chains to lie slightly close together to increase its melting point so it becomes more solid, okay? So that is what we call by hydrogenation, adding hydrogen and hardening that oil into maybe a butter, for example, okay? So we've looked at where we can get oils from and why they're useful. Okay, so in terms of cooking at higher temperatures, for faster cooking, different flavours, but it increases the energy content of our food. We've talked about unsaturated vegetable oils containing carbon double bonds, so they're alkenes, okay, and we can detect that with Brayman water. We can turn some of those oils into harder butters and margarines by adding hydrogen, getting rid of the double bonds, making those chains straight so they lie close together, increasing the force of attraction and therefore increasing the temperature which we can melt them. Then we finally looked at the emulsions, so the fact that the oil and water doesn't mix. By adding an emulsifier, we tie them together, if you like, with that hydrophilic head and the hydrophobic tail, tying together the oil and water, so we get a thicker solution used for salad dressings, ice creams and paints. Okay, so that's the end of C1, part 8.